So, good afternoon, good day, good morning, friends, depending on where you are. And this is Anirban. So, I have planned to share some of my experiences in implementing live artificial intelligence projects in areas like computer vision, NLP, and also predictive analytics on numerical data. One of the reasons I thought of doing this is what I found is after doing number of courses and certifications, when we get down to the real world implementation, I found the real world problems to be much more challenging than what is given in most books. And it's very important to follow the proper process in a scientific way and give the business users the results that they are looking for in a proper way rather than doing something quickly. So with that in view, I thought of sharing this set of best practices, and let's see how good they are. I can say they are best practices or good practices so depending on what you may think, but definitely it's not that it is only my viewpoint. All these good practices or best practices have been derived by intense discussions with senior data scientists in various organizations or my supervisors in my organizations where I work for. So these are well established principles which I would like to share. To start with, today I'll talk about image classification. And image classification, I think, is one of the first problems that we do in machine learning and machine vision, computer vision, right? So we have all done the MNIST handwritten digits image classification, right? But the whole problem is no real world problem I've seen that comes with uniformly sized images of 28 by 28 xy dimensions, width and height, 28 by 28 pixels, all of uniform size. No, it doesn't come like that. Or very clear images in a black background showing the digit, handwritten digit. It doesn't come like that as well. So then what happens is any real world problem I've seen that we have to try out multiple techniques. No one technique we can just take from the book and implement. I have not seen in any of the projects. We have to keep on trying multiple techniques. So what are some of the techniques we should look at when we try to do an image classification problem in the real world? I'll go through a brief overview of some of the techniques and then go into in detail into one of the technique by showing some working code as well, right? So definitely when it comes to image classification, some of the first things that come to mind is using transfer learning, where we use a pre-trained network and add fully connected layers on top of it and custom train it for our own use case. And then transfer learning, when we say which pre-trained network are you going to use? So here there is no clear answer, and I think we shouldn't restrict ourselves to any one network. We have to keep on exploring. It could be, for example, VGG 16 or 19. It could be Inception V3. It could be ResNet 50, right? It could be DenseNet 121. So it's important to try out all these various possible combinations, and it's important to know and to note that each of these pre-trained networks have their own input sizes. So they don't all follow the uniform image size as input. So most networks have a size of 224 by 224. Some has size like 299 by 299 as the input image size. So one of the first things that we need to do is image resizing, because we need to feed uniform image size to the pre-trained deep learning model. So, how to do transfer learning? I'll come back to that. What way to do the transfer learning in the best way that I have seen? I'll come to that. But before even going there, I would like to talk about image resizing to some extent. And when we talk of image resizing, I mean, sometimes we don't even notice it that much when we are working with MNIST images or some other images which are very uniform, with a black background and a white foreground showing the handwritten digits, things like that. We can resize it in any way, it doesn't really matter, but not so in a real world problem. So why I'm saying this, so in a real world problem, in a recent classification problem that we did for one organization, which is a top five global organization in the pharma industry. So we were doing an important problem, and obviously I cannot give the details of the problem. But what I would like to share here is the images that we are classifying. They were varying in sizes. So there could be some images which are like maybe 30 by 30 pixel, and some images could be 500 pixel width and height. So with such a varying range of image size, how do I bring it to a uniform size? Do I simply say image.resize that will do the work? It's not that way. So I'd like to explain by a code sample over here. And so this is my notebook, which is shows image resizing and image augmentation. What's very important here is while resizing, we need to understand what is my strategy of resizing. So one of the good practices is when the image size is less than the target size, it is always best to use. I mean, it all most of the time it works much better to use a zero padding, right? And when the image size is higher than the target size, we need to basically resize it. But what is also important there is the interpolation method. And what we have found is the Langsauce filtering method for interpolation when downsizing the image has worked best. And I think that is one of the best methods available. So this example shows how we can resize the image, right? And we make a check when the image comes in with the width and height. If it is less than my target image height, we find out the the delta of the image width minus the target image width minus the actual image width, and then we find out the pad width, and we do a padding where we do a image ops dot expand the image with the padding. And here, what we have seen, the PIL library works the best in this scenario. So, one thing we need to note is when we are doing a real life problem, it's not so simple as just download some data set from TensorFlow data set, apply everything, just do a feature, scaling, and just pass it through the network and done. No. So we might need a combination of techniques from different libraries. So here you can see that we are using the PIL library, we are using the TensorFlow, we are using the scikit image, and various other things for uh, augmenting the image and resizing the image, right? So for this operation, the PIL image library is the best suited, and one can see the reference of the image ops.fit in the PIL library documentation. So that is what is being used. And what's also very important is when we are augmenting the image. So how do we augment the image? So let's say we are doing a contrast enhancement or a brightness enhancement. Do we do that before resizing the image or after resizing the image? That's also a very important consideration, right? So I'll show that also. So coming to the image, so I'm using a flower image here, right? And we can see this is the flower image. So initially what we do is using OpenCV, we just read the image and we see what's the width and the height of the image, right? And we create image objects by doing the TensorFlow Keras utils load image function, where we give the target size. Now this is important. Sometimes we have done the mistake where we just give the target size as the target height and width, and so the image when loading it gets loaded as a target height and width. But that's not a good practice in my opinion, and that's what we have found. We should resize the image the way I have shown, uh, depending on whether the image is higher in bigger than the target size or smaller than the target size. If it's smaller, we do a zero padding. If it's higher, we do a downsizing of the image. And it's also important to select carefully and try different filtering techniques, interpolation techniques. Here we are using Langsauce, which has worked best for us, and you can experiment with different techniques over here. So if we see here the image, we are printing the image height and width. It's uh, 256 by 256, and so what I've done is I've loaded the resized image, right, using this image, original image. And as we can see that here, when we are displaying the image, we can see that it has added a black border around the image. We have loaded the image in grayscale, and we could have loaded it in color mode also. Uh, so if we just don't use the grayscale, we can load the image in the color mode. It will be a 3-channel image, and we can. So we can see that there is a black border that has been added. The image is 256 up to here, but around this, a black border has been added. So that is the important thing that I was trying to show. I'll switch back to the grayscale image for now because some of the augmentation techniques may work better, like the histogram, adaptive histogram equalization, and all that. So that's why I'll switch back to grayscale image right now. It can be done with a color image also, most of these techniques. So when I flip the image or when I do a contrast adjustment on the image, let's say, so it's important that the contrast adjustment is done on the original image and then the image is resized using the resizing technique I talked about. Because try to understand that when we are doing a contrast adjustment, right, it doesn't make any sense to do a contrast adjustment on the black padding, right? It will not help in any way because that's not a information which is useful to the classification process. Or if we are using noise, we are using Gaussian noise or blurring or something, it doesn't make any sense to introduce that noise in the black padding outside the image. So it's important that we resize the image after doing the enhancement to the image. So this is where we are adjusting the contrast. And if you see here, here we are using the TensorFlow library, tf.image.adjust contrast. And this is a factor which adjusts the contrast. You can vary it, you can see the result, to what extent you need to adjust the contrast. So this is another result with this factor as 4. So and we are just visualizing the original image and the contrast adjusted image. So there are two things to multiple things going on here. One is using the TensorFlow library right over here, and the second thing is we are resizing the image after doing the contrast adjustment on the original image. So this image array is coming from here, which is the original image array. And what's more important is we load the image in TF Keras using the original height and width, not the target height and width. This is very, very important. And in fact, I remember we made this mistake. We were loading the image with the target height and width, and so the image gets distorted. So a small image, which is, let's say, 30 by 30 pixel, when I load it with 224 by 224, that image gets distorted. The pattern is not correctly there, and we get a much lower classification accuracy. We face this kind of problem. So it's important to load it in the original size, do the enhancement, and then resize the image. So now it has become 299 by 299, but the augmentation is only on the image which was 256 by 256, not the black part, right? The same way, when we are flipping the image or we are rotating the image, we can think of it the same way, and we can do it the same way, right? Brightness adjustment, or so this is a brightness adjustment, right? Same principle holds good, right? And so if we want to use something like a Gaussian noise, we can use the random noise of the scikit image with a mean and variance over here. We can even use the salt and pepper noise. So the mode can be changed from Gaussian to salt and pepper in the random noise method of the scikit image. And depending on this mean variance, we can have different types of Gaussian noise and different types of salt and pepper noise introduced over here. It can be seen here. So as can be seen here very clearly in the second image, this is a very too much salt and pepper noise has been added. And where these noising techniques are needed, I'll explain that. It's something called test time augmentation, which we have used in one of our projects. And I'll give the reference to those research papers also. But what I'm trying to say here is, the point I was trying to make clear again and again, that the salt and pepper noise is applied only to the image in the original form, not to the resized image. So the zero padding or the black border, you can see it is not adding any salt and pepper noise, because I am doing the salt and pepper noise, random noise, on the original image. So apply noise on original image and then resize, and then I'm doing the resizing. And since the image size is less than the target size, height and width, I'm using a black border. So here also we were making a mistake. When we didn't know, we were doing the salt and pepper noise all right, but after resizing the image, so which means this black border will also have the noise, and that's not something very useful to me. Now, why we are introducing this noise, if somebody may ask that how it is going to help in image classification process. Yes, for a normal scenario, MNS digits, we may not need it. But for difficult cases, we might need to add various noises in the image and use that in the training data. And while doing the prediction also, we do the same noise generation on the images. So for example, if I'm using Gaussian and salt and pepper noise in the training data, let's say for each image I've created two images with noise. While doing the inference and checking the accuracy of the image, I'll not do the inference straight away. What I'll do is I'll do an inference on the exact same way noise generated images, Gaussian noise and salt and pepper noise, with the exact same amount of noise which is given here. And then what I'll do is, for each image I will take the mean of the predictions of these noised images and use that as a prediction. Mean means the majority vote over here, because this is a binary classification. If you're doing, let's say, so we'll take the majority vote, which if the noisy images, what are they classifying? What is the target class I'm getting in a majority of the cases, and that I will use as the final prediction. This is called something called test time augmentation, and I'll talk about it in detail later. But just to give the context why we might need to introduce such noises in some cases. Similarly, histogram equalization, as we can see here, we are doing histogram equalization over here. This is something that, as far as I understand, it works mainly on grayscale images. Some the other images, the other techniques like rotating and zooming, panning, all those things can be done equally well on color images, and I would like the viewers to try out that definitely. Histogram equalization is something, it can be done on color images, but I think it's a very complicated thing to do. So here we are using the OpenCV equalize hist on the image, and we can see that the original image and the histogram equalized image are available here. And again, the same thing, coming back to the same thing, you see the black padding is there as it is. That is not being passed to the histogram equalization, because the load resized image is working after doing this technique. And we can do the adaptive histogram equalization as well. So this is the output of adaptive histogram equalization using the OpenCV Clahe method, right? Where so now it's important to note that we need not, when enhancing the images, we need not restrict ourselves to one technique. It could be scikit image, it could be OpenCV, it could be TensorFlow. We can use all these things, and get our image array. Once we get our NumPy image array, I mean, it can be used in our training or prediction or inference, wherever it is. So we have used histogram equalization, adaptive histogram equalization, and we are doing the adaptive histogram equalization once again here with a different parameter, which does which uses a different, the area over which it's going to, different dimension of the window, which over which it's going to do the adaptive histogram equalization. We can see slightly different results over here, right? Gamma correction is also another important thing. We are using that from the TensorFlow library. So we have to be imaginative and do the techniques depending on the library where we can get it easily, right? So gamma correction, adjust gamma, is there in TensorFlow very well. So let's use that, right? Poisson noise. Now, Poisson noise, it may be there in scikit-learn, scikit image. I am not very sure. In this scenario, we are using a custom method to introduce Poisson noise, right? And we can visualize the original image and the augmented image, which is having Poisson noise. And we can write these images into the disk if we need, using cv2 dot I'm right. So the point here that I was trying to explain today is, one is, we can augment the data using different techniques like histogram equalization, adaptive histogram equalization, Gaussian noise, salt and pepper noise, brightness enhance, contrast enhance, right? We can use a mix of different libraries. It could be TensorFlow, it could be scikit image, it could be OpenCV, and we should not be limited to any one library, because my purpose is to augment the image. Whichever library gives me that facility, I will do that, right? There's another very good library, as we all know. It's called the PyTorch Albumentation library, and I can discuss that on a different day. On the next session. So here the important thing that I wanted to show is not only about this augmenting the image in various ways. How do we resize the image, right, when the image size is varying a lot, right? So we may have different target sizes depending on the on the network transfer, on the pre-trained network that we are using, right? Some of these may have 224 by 224, right? Some of these could have 299 by 299. The target size can vary, isn't it? So in such scenario, how do we resize the image? And we discussed that if the image size is less than target, we zero pad, else we the image and use the appropriate interpolation. So this appropriate interpolation technique can be seen over here. So this is the thing where the basically it's available in the pillow documentation, image ops.fit. So, right. And this method is what I was talking about, the method of and it can be different filters can be used. So default is bicubic. What we have seen is in our case the lang sauce filter worked good for us. So I'm not saying that will go good for everybody, but what I'm trying to say is we might need to experiment with this also as one of the important factors while doing this. And you can see the performance and everything, downscaling and upscaling quality of the lang sauce is shown as one of the best. So that is important. That those are the important things I wanted to talk about, which I've learned from experience. That depending on the target size, how do we size? And the most important thing is when we are adding this, when we're doing the image enhancement, it's important to do the image enhancement on the original undisturbed size of the image, and then resize the image. That's also very important. I mean, for experienced practitioners, this may be very simple, this thing, but we had to learn it after doing the mistakes, and that's why I particularly thought of sharing this video. So I didn't quite time it today for the first time. I hope it was useful, and what I'll do is uh, I'll share this image and this notebook as well in a GitHub repo and share it along with this blog. Thank you so much. Thanks for viewing.